we continue now. We start with today with the concept which is called subspaces. This is the development of the ideas of the vector spaces we discussed with you last week. To some extent, dealing with the subspace is a lot easier than dealing with the spaces, because look at this. Let's just first discuss what the subspace is. So you always start with a quadruple like this. You always start with a quadruple like this. You have a vector space, some abstract vector space, and when you look at such quadruple, you can always keep in your head those fundamental examples we discussed with you on Thursday last week. So subspace, so this is a vector space. Subspace, in order to identify or define a subspace, we start off with some subset within this vector space, this symbol. You read this as a subset. You call this subset a subspace. That's the difference. If and only if you build a new quadruple where you replace your original vector space with this subset S, and you borrow the rest of the elements of the quadruples, you just take them literally. You call this new quadruple you call this new quadruple a subspace if this quadruple by itself independently is a vector space. So if this quadruple by itself independently satisfies all of the 10 axioms we discussed on Thursday. At first, when you think about that, you may say it's a huge job actually to test to test subspace to be a subset to be a subspace, because you have to go through all of the 10 axioms. In reality, when you deal with the subspaces, it is a lot easier, because we have what I call a subspace lemma, or in fact here on this slide I call it a subspace theorem. I decided to call it a theorem because of an importance of this result, because of how often you're going to use this result in many questions in the yellow book. It says this: a subset S will be subspace in these terms if and only if, this writing IFF, you extend it as if and only if. Yeah, if and only if. I used it once already. A subset S will be a subspace if and only if the following criteria satisfied. The following criteria are satisfied, and here are the criteria. There will be 3 of them, and that's already a relief, because in a direct verification you need to do 10 criteria, 10 axioms, whereas when you test for the subspace you need to test only 3, but those 3 you will need to test every time you look at a subspace. So the first one, as easy as testing whether the zero vector, which was originally in your V vector space, is in S as well. If it is not, it's not a subspace straight away. The second one says if you take 2 elements of your proposed subspace, then it must be that when you add them up, and you can add them up because these elements, they also from this larger vector space, which we given that it is a vector space, the sum must be in the subspace, in a subset as well, or in the proposed subspace. And the third one says whenever you take a vector and whenever you take a scalar, if you scale that vector with a scalar, you will end up in a subset again. So basically, the 3 requirements you need to check. First one is that the 0 in the proposed subspace. Second one, you can call it shortly that this proposed subspace must be closed under addition. At this stage, I think the idea of something being closed with respect to an operation must be quite familiar to you. And the third one is that the S is also closed under scaling by any scalar available in your vector field, scalar field. If these 3 criteria are satisfied, you can safely claim that your S is a subspace. There will be plenty of examples in the yellow book where you would need to follow these steps. You would need to check that some subset is a subspace. If you already attempted, which I doubt, verifying all 10 axioms by yourself, you will realize how much an advantage of dealing with the subspaces rather than with the spaces themselves, where you need to address all 10 axioms. Even if you exercise very good structural approach with the 10 axioms, it's quite a job to check all of these 10 axioms. Whereas with the subspace theorem, it's just free, you need to address. I'll show you a few examples. In fact, dealing with the subspace is even easier than this, because almost every example in the yellow book will fall into quite limited number of categories. In fact, two and a half categories. The third one will be half a category because it's not an independent. It will rely on the first two. And I'll discuss with you these categories. If you master these 2.5 categories, all of the examples in the yellow book will be like a piece of cake to you. But it's not an easy mastering this in the generality. No, I don't mean to scare you. They're not that hard, actually. Any questions? So the first category of examples, and I'll discuss this exactly as a general category. Many particular examples in the yellow book will fall into this category. Here it is. I think it should be this one. No, my apologies, it's the wrong one. Yeah, it's this one. That's a slide which I call example of a subspaces, even though there will be other slides where there will be another example of a subspaces. I took two examples from the yellow book as demonstrations, but I will show you how these two examples fit into the general category number 1 of type of subspaces you potentially meet in the yellow book. So this is the example. So it's a set which I call S1. It's a set which I call S1. It's the all triples in R3. Remember, R3 we know now, we can refer to that as a vector space. All triples such that the components of those triples are subject to the relation like this. In fact, it's tutorial question 17. So here we follow this ubiquitous convention that the vector which is labeled X has components labeled by the same letter X with indices 1, 2, 3, 4 as much as needed. In this case, because we're looking at triple of numbers, we need 3 such letters, X1, X2, and X3. So question 17 in the yellow book says check that this is a subspace. Right. It says check that this is a subspace. I will show you which category, and now I will show you the category where this example fits, and I will call this lemma. There will be two parts in this lemma. We're going to discuss the first one. I call it the alpha part, or A part if you don't like Greek letters. Look at this example. This symbol, and I suggest you remember this notation. I'm going to use these notations quite often in our joint meetings. S sub R and the vector A inside represents collection of all n tuples such that when you take a dot product of these n tuples with a fixed n tuple A, you end up with 0. A is a fixed n tuple. Okay? Why did I make such a category? Well, why did I introduce this symbol? Because this particular example from question 17 perfectly fits into this template. All you need to do, you need to choose the A n tuple correctly. What should I take for the A here in order to make this example or this set turn into this set? Here. S1, this original set S1 from the question 17, It is this type of sets if I choose for my A vector this triple, 3, 2, 3, and negative 4. If I choose in place of this A here 2, 3, negative 4, this dot product, I hope we remember how we compute the dot products between n tuples, right? We multiply per component and add them up. That's how we compute dot product between two n tuples. If you do these computations here, with this choice for the A vector and x1, x2, x3 for the x vector, you will end up with this relation straight away. So, my example 17 perfectly fits into this general scheme, right? So if I argue this general scheme rather than particular example 17, later on any other example which fits in a similar fashion into the scheme, I can do them by just making a reference to this lemma. And that's what I'm going to do very often. So I will argue this general scheme with the abstract vector A rather than particular chosen vector A, and then I can claim any other example which fits into the scheme follows from the general argument by reference to this lemma. It's very typical what we do because we're very efficient in mathematics. That's why we see the patterns, we see general rules, we argue generally, and then make a reference in order to save time, writing, effort, muscle pain in your hand or ink in your pens, whatever suits you. We'll just do this. So lemma claims that this is a subspace no matter how you choose your A vector. And here's the proof. Like I said, every time you argue something is a subspace, and you will be doing very often this type of argument, you have to address those three criteria on the slide before. You need to show that zero vector is in this chosen set, in the proposed subspace. You need to show that it is closed under addition. You need to show it is closed under scaling. So here we go. By subspace theorem, my proof is based on the subspace theorem from the slide before. I argue the first criterion from the subspace theorem. I need to convince you that 0 is in my set. In order to argue this, all I need to do, I need to see if this relation works for the 0 vector in this place. But it does. Because again, if you refer back to the way, if you refer back to the way we do dot products, if you take a 0 vector here, which we know the vector which carries all 0 components, the dot product will make it just 0 number. So 0 vector perfectly works in this relation, and that's why I can conclude that the 0 vector will be in a set like this. It's a very short argument based on the properties of the dot product. Second criterion, sorry. I start with 2 vectors in my set. I now will interpret what it means to be in my set. That's exactly what it means to be in my set. So here's my interpretation of X being in a set. Here's my interpretation of Y being in a set. This step in my argument came from the fact that I'm just doing the interpretation of something being in my proposed subspace. Now, the next step, it's the key step in the argument, it will use the distributive law of the dot product, something I assume you know from your experience or from your study of the dot products. If your dot product a vector with the sum, this is as good if you dot product a vector with them individually, and then you do the plus. By the way, it's another instance of this multifaceted plus sign, because here the plus, it's the it's the n tuple plus, here's the plus, it's a numerical plus. Think about that. Because x came from the s, this is 0, if you add 2 zeros, it is 0. If I now interpret this relation, again in the context of my proposed subspace, I can claim that x plus y in my set. Similar argument works for scaling. Third one. if I start with the scalar in real numbers and a vector in my set, first I do the interpretation, what it means to be in my set. So I just use this condition on my vector. Then I will use the properties of the dot product, which says that if you dot product a vector with a scaled vector, this is as good if you first take a dot product and then you scale the result. Again, I draw your attention to the multifaceted nature of a dot here. The dot in here between lambda and x, it's the scaling of n tuples. The dot here between lambda and a bracket, it's the numerical multiplication. Even though it's the same writing, totally different meanings. The result is 0, of course, because if you multiply any number by 0, it is 0. And that's now, if I interpret this relation, I conclude that my scaled vector x is in my set SRA. And that's why any set of this structure is a subspace. I can use this now freely in all of these subsequent slides in all of my subsequent slides. In particular, this S1 from question 17, because it perfectly fits into this general template, it is also a subspace by this lemma. Given that I'm going to use this lemma so often in the subsequent slides, I will give a name to it. So every time I tell that name later, I will be referring to this lemma. You should remember that in order to facilitate your understanding of what's happening in class. I'm going to give a name to this lemma in order to make it easier to make a reference to this lemma later. Okay? So the name, if you finish with the taking notes of the proof, even though I'll publish these notes on the website as I normally do, I'm going to call this lemma orthogonal complement subspace. This kind of templates or this kind of subspace, I'm going to call them orthogonal complement subspaces, and the corresponding lemma will be called lemma of or regarding orthogonal complement subspace. That's the name I'm going to use to make a reference to this lemma in our future meetings. And you have to remember that, because otherwise you won't be able to follow entirely to our discussion. It's a very powerful lemma. It covers, like I said, there will be 2.5 categories, so it covers one whole category of the examples. Percentage-wise, how many is 2.5 out of 10%, or 100%, sorry? 40, isn't it? You're supposed to be financial people. You should have supposed to compute percentages very quickly. 2.5 out of 100 is 40, isn't it? Without the calculator. So this lemma covers for 40% of the examples in the yellow book. Even more, actually. Given that this half of the category, it will rely on this lemma as well. Right, and that's how we do question 17. There's another question next to it, question 16, which takes this example, S2 I call it. It looks a lot like the one we just done, but the difference is 6 here. This is a kind of thing we can argue almost instantly, because if I want to see that this is a subspace, I need to check all of these three criteria. This thing doesn't fit into this category, so we cannot do this example by making reference to the orthogonal complement subspace lemma. We cannot do that. But if you try to argue this directly, you will realize almost instantly that the zero vector doesn't belong to this S2. Because if you try zero vector on the left-hand side here, you will end up with 0 number, which is not equal to number 6. And that's the reason why this S2 fails first criterion of subspace theorem. And that's the reason I can immediately claim that S2 is not a subspace. So here's a demonstration to you what you have to do if you need to argue otherwise. If you need to argue that something is not a subspace, you need to fail one of the categories. And you fail those categories by giving, listen carefully, numerical counterexample. Nothing else is work. No matter how much paragraphs you write, why it doesn't work, nobody gonna take this. only numerical counterexample does the job. So it is your task, if you believe that something is not a subspace, to come up with a counterexample which shows that one of the criteria is not satisfied. In this case, is my numerical counterexample. Zero vector, it's quite a numerical vector. In some other examples, you would need to disprove 2 or 3, where you would need to come up with a numerical counterexample. And actually, that's a general rule of thumb. When you disprove something, you're supposed to present a numerical counterexample. All other things, very subjective, and no one will believe you, especially when it comes to the exam. Any questions? Well, given that I call this part alpha of my lemma, there is another part, which is very similar. I call it part beta. And that's a very similar construction, but not within the n tuples of real numbers, but within n tuples of complex numbers. Very similar construction works. And that's a different notation. See, I use the subscript C here to indicate this time it's the n tuples of complex numbers. A construction like this, the rest is the same. N tuples of complex numbers, which are subject to this relation, where B is a chosen or fixed n tuple of complex numbers. Every construction like this will be a subspace. The proof follows almost identically the same argument. If you like challenging, or if you like training yourself, you can try to reconstruct the proof. It's not really a big deal. I will rely on this part as well if it comes to complex n tuple subspaces. Okay. Right. So this is the first half. It's one of these 2.5 categories. 2.5 categories. There will be a second category, which is to some extent, it will be a little bit harder for you to grasp that category. It's a little bit more abstract, but like I said, it's another 40% of the examples in the yellow book. But before we do that, I'd like to discuss this half of the category, which relies on the first two. It's my next, yes, it is my next slide. Let's just look at this. The slide is called intersection of subspaces, or intersection of subspaces lemma. It's another name I'm going to use for reference very often. I mean, the lemma we're about to discover. Later on, I'm going to use this lemma very often to make my presentation shorter. And it is your part of, it's your contribution to success of these meetings to remember the name of this reference and what it's referring to. So, in fact, I mean, this lemma is given as a tutorial question 32. So it's not a question we can do together. It will have two parts again. It says this: if W1 and W2 are two subspaces, that's the kind of categories we now operate with. If you have two subspaces, W1, W2, so two subsets which are subject to three criteria we just discovered through subspace theorem, then if you build a new subset by taking intersection, meaning that we take the common part of the vectors which belong both W1 and to W2. If you take intersection, this new construct will be a subspace as well. And that, if you believe in this, that opens the whole lot of possibilities of building new subspaces. You can take one of the subspace of orthogonal complement type from the slide before. You can take another one of the orthogonal complement type. You can intersect them, it will be a new subspace. You can intersect this again, it will be another subspace. So this little lemma in equation 32, it opens huge possibilities in construction new subspaces. All you need to do, you need to take intersection of the existing subspaces. And that's what I call a half a category. Even though this half will cover cumulatively more than the first two categories, but it relies on the first two. So the first two, it's a primary categories. One of them is the orthogonal complement subspaces we just discussed with you. The second one is still coming. The second one is still a mystery, but I will show you this. But this one gives you the possibility, by playing with the first two, build new subspaces. Lemma has a second part as well, which just tells you if you have not just one, but the whole sequence of subspaces, W1, W2, W3, W4, and many others, if you take, and all of them are subspaces, if you take just one huge intersection of those, one single common part between all of them, that will be a subspace as well. This is of course mathematical induction development of part alpha. So the principal argument, of course, here in part alpha. To do part beta, all you need to do mathematical induction principle. So we're not going to argue beta, but we will discuss alpha a little bit. In fact, this is the question 33 part A, in fact, this version. So like it or not, but if you need to prove something as subspace, you need to go through the subspace theorem. You need to go through these three criteria we listed very first today, at the very first slide today. There's no any other option, and again, you will do this quite a few times through the yellow book. I need to do it here as well, to argue this alpha part of my intersection of subspaces lemma, I need to go through this category. So I start my proof again by saying, by subspace theorem, I would need to argue three criteria. If it's missing. First one says, if you remember, first one says, and trust me, you need to remember those three criteria. You can't avoid that. Right now, I can expect you to remember, but by the next meeting, you will need to remember that. First one was the criterion which required 0 to be in the proposed subspace. So in this case, this is a proposed subspace. That's the one we're testing to be a subspace. These two are given to us, they are subspace. So we're going to exploit this, what is given to us, in order to achieve intersection to be a subspace. So here we go. We start with what is given to us. W1, W2 are subspaces. So in particular, by subspace theorem, 0 vector must be in W1, 0 vector must be in W2. This is because W1, W2 are subspaces. Due to the nature of intersection, it's a common vectors. It's a vectors which belong both to one and the second one. Because 0 belongs to both of them, due to the nature of intersection, 0 belongs to W1, W2. Well, actually, I use the name W here because let me just call this W. One of you once asked what I mean by the colon. If I put it next to the equal sign, it means that equal by definition. So I just define the symbol W to be this intersection subset. And that's the end of the argument, you see. We just use the fact that W1, W2 by themselves are subspaces. We use the nature of the intersection. And that's all we need to do. That's all we need to do to argue part 1. Part 2 follows almost the same steps. We take two vectors from W. Our objective is to see that if you take a sum of these two, it will also be in W. That's our objective. And here's my steps which lead to that objective. Look at this. First, because something belongs to the intersection, it means it belongs to every part of that intersection, right? It's just interpretation of being in the intersection of two sets. This is just interpretation of being in the intersection. If X belongs to intersection, it belongs to W1 and W2, and the same goes for Y. Next step leading towards the objective is that because W1, W2 individually they are subspaces. For them, second criterion of the subspace theorem is satisfied. So I can claim now that if I add the x and y, it will be in W1 because x in W1 because x and y in W1. And the same claim can be done about W2. This is because W1, W2 are subspaces. And then I make another reference to the intersection. If some vector, in our case, x plus y vector belongs to W1 and W2, it will belong to an intersection of W1 and W2. And that's why we come to the objective. Every step is perfectly justified. It is very clear where in my steps I use the assumption, and that's the assumption of the lemma. I made it very clear where this worked here, as well as I made it very clear where here it worked here. When you present your arguments, you should exercise the same caution and the same structure. You have to make very clear where the assumptions are used. You cannot make an argument from scratch. Nobody can. There's always something you rely on, something in your background, something in the reference book, something in the yellow book. There's always something. Your job is to make this something explicitly visible. No one makes proofs from scratch, trust me. Any questions? Well, there's a third part. There's a third part here. I'm not going to show it to you. I'll leave it. I suggest you try to figure out the steps independently. If you struggle with that, there will be complete notes uploaded on the web within next 2 days. You can refer to them if you are unable to recover those steps. But from now on, I'll put now another little, actually quite powerful tool in my bag of tools, which I'm going to use later. First tool was orthogonal complement subspace lemma, the one on the slide before, and that's the name I'm going to use to refer to that. The second tool, which I'm going to use, is the intersection of subspaces lemma. With these tools alone, we can do a lot, in fact. With these tools alone, we already can do a lot. Look at this. Because it's a 1.5 category, so it's 60% of the examples in the yellow book. 60% of the examples with 2 slides, if you know how to use them. It's huge. All you need to do to learn how to use them. Here's the example how to use these two together. I call this slide intersection of subspaces example. It's example 20 in the tutorial book. That's a set S, which we need to argue it is a subspace. Look at this. It's very similar to the one we saw in my first example, yet it's different. It says take all of the triple of numbers, real components, such that these two expressions computed, both of them simultaneously 0. That's the example in question 20. We need to argue that this is a subspace. With the help of these two tools, it's a 2-line argument. So the first line, well, 2 or 3 lines argument. The first line I'm going to say is this. I'm going to split this condition in 2 conditions. So I'm looking at all of the triple of numbers which are subject to this long relation. Or equivalently, I can say, I'm looking at the triple of numbers which are subject to 2 simultaneous relations. One of them like this, and the second one like this. So in fact, this one single relation, or the collection of triple of numbers which is subject to this long relation, this is as good as intersection of the collections which are subject to these individual relations by themselves. That's a key idea. That's the key idea where the intersection comes into the picture. If you take a triple which belongs to this set and belongs to this set at the same time, it is as good as the triple which belongs to this set with this long condition. Here's my intersection sign, which makes it work. Let me make it larger. Here's the intersection sign, which makes it work. Now, individually, this piece and this piece, they perfectly fit into the orthogonal complement subspace lemma scheme, isn't it? All I need to do, I need to choose that A vector properly. And for this one, the A vector, here is my choosing. For the first one, the A vector is 2, 3, negative 4. For the second one, the A vector 4, negative 2, and 3. If you use these two vectors on a slide which is called orthogonal complement subspace lemma, you will see that this set perfectly fits into that scheme with this vector, and this set perfectly fits. This set, yeah, that's right. This set is perfectly fits into that scheme with the different vector though, but who cares? We argued that scheme for any vector. So now I can say this bit is a subspace because of the orthogonal complement subspace lemma. This bit is a subspace because of the orthogonal complement subspace lemma, and the whole piece is a subspace because of the intersection of subspaces lemma. Making 3 references in one sentence finishes the whole argument. You can't deny this is a beauty. It will save so much time, to me of course, and to you if you know how to use it properly, which is a harder task, and yet it's very rigorous and very formal. We're not missing anything. We're not leaving any crack for the mistake. It's just the hugeness of those 2 templates we developed on the 2 previous slides just helps to cover so many examples at once. This is the beauty of the mathematical reasoning. Developing this, seeing these patterns, developing these patterns, and then applying these patterns, that's what the mathematics is about. The harder part, of course, seeing the patterns. This is only very few of you will ever master, but it's not actually part of the assessment in this topic to develop skills which help you see the patterns. The least we expect is just to be able to use the patterns, which are already shown to you. Any questions? Okay, I think we have enough time to discuss the last category. We have about 10 minutes. I think it will be good if we discuss all of the categories in one lecture. So later on, when you revisit this, you will have this accessed through one single video with one single bunch of notes. I'm saying this because, in fact, this slide, I didn't open it for you, but this slide has another example where the same methods are used. It's just the example from the yellow book where the proposed subspace split into orthogonal complement subspaces and combined with intersection. You will see this example if you download the notes I will put on the web in a few days, but it's just the same scheme. In fact, I encourage you to do it on your own. Practice this straight away, seeing the patterns and applying these patterns. Rather than discussing the second part of the slide, I'll go straight to the last second category of a subspace, which covers the remaining 40% of the examples. Here it is. Unless you object, of course. Matthew, was it? You don't object, right? Good. This category is called span subspaces. That's another name. It's another name for reference purposes. Besides, it's a new thing to you, I suspect. Yeah, that's my second category. So right now we call it 1.5 categories. That's the second one. Again, we start with the quadruple. Quadruple, which represents general vector space. Again, you can keep in mind this, how many we had? Like, we had 4 fundamental examples on Thursday last time. So look what you do. So this is a vector space. We choose actually n vectors, and this time this S has nothing to do with the subspace. This is just finite set of vectors n. My choosing is n here. So it's not a subspace by itself. It's just n chosen vectors, and you're free to choose anyone, any vectors. Different choice will make a different span subspace. The span subspace itself, it's a construct like this. It's a symbol, which you will see very often, span of this finite set, S, and the span consists of the following structure. Look at this. You take combination of this type. So you see what I do? I take the vectors I chose, x1, x2, xn. I multiply them by some scalars. There's a typo here, supposed to be lambda. I'll fix it in a second. Scalars are, they are free to be anything from your field of scalars F. Let me just fix this typo. It's a typo. So you just play around with these scalars. You choose them any way you wish. You keep your vectors fixed. You don't touch them. You make a choice before you started constructing your span, but you don't touch them. You just do all of this choosing for lambdas. You just choose them any way you wish. You will end up with a huge collection of results. You hardly can actually list them all because there will be infinitely many choices for this coefficient, infinitely many choices for this coefficient, infinitely many choices for this coefficient. So there will be infinitely many combinations like this all together. As a class, it is called span, and it is a subspace. And that's something I'm going to call span lemma. Span of S is always a subspace. Span of S is always subspace. The combinations of this type, again, to make language easier, your language in the first place, because you're going to come to us or you're going to discuss it between yourselves, discuss it with your tutor, different things, different examples, and the sooner you start using the proper language, the quicker your tutors or your correspondent will understand you. So this thing, the name which we normally often use for the combination like this, is called linear combination of vectors of S. It's not a term which we expect you to remember. Or on the convention side, actually, if I ask you, if I take a span of an empty set, what do you think that will be? Given the definition of the span like this, what should we convene to believe span of empty set be? Huh? That would be a very bad choice of a convention, because empty set is not a subspace, isn't it? Whereas we have to make a convention, of course. You can't really argue what it is. You can't prove it. This definition doesn't cover for that. The definition assumes that S has something in it. So we need to make a convention for the span of empty set. But when we decide what kind of convention we're going to make, we need to make a convention which goes in line with the things expectable from span. And one of the first things which we expect from span is to be a subspace. If you make this convention, this is bad convention. It doesn't go in line with this one. Empty set is not a subspace, because I'll give you a chance to speak in a second. Because it fails the first criterion of a subspace theorem, isn't it? Zero vector doesn't belong there. Zero vector doesn't belong in empty set, so that's not a subspace. It's a bad convention. A better convention will be Is it a good convention? Not really. Because this is supposed to be a set. This is not a set, isn't it? What probably you meant to say, you mean the right thing, you said the wrong thing. That happens to you very often, actually. You mean well here, but the thing which comes out of your mouth is just horrific sometimes. And you should work on that, as a matter of fact, because that will make people understand you better. I mean, we make an effort and we try to read your mind even though you say the wrong things. It's just because we have a lot of experience of dealing with students. But if you go out on the street with a person who is not experienced with dealing with this, he will not understand you. So what you probably meant to say is that a set which consists of one vector, zero vector. Is that right? Yeah, that will be the proper say to say. So the convention for the span is, you're going to work a set which consists of one single vector. And this set will be a subspace. You can argue this. The only way to argue this, as a matter of fact, through subspace theorem. You need to test three criteria of a subspace theorem. You need to see that 0 belongs to this subset. It does. We just made it so. You need to test that if you take two elements of this subset and if you add them up, the result will be in here. It's very easy check because if you take two elements, the only choice you have is 0 vectors. If you take two 0 vectors, if you add them up, it will be a 0 vector again in your subspace. And equally, if you take a vector and if you take a 0 vector, the only vector which is available to you, if you scaled it, and if you put the result will be 0 vector, so it is again in your subset. That's why a set consisting of one 0 vector is a subspace, and it's the smallest possible subspace, and that's a good convention for a span of an empty set. Keep this in mind. We cannot prove this, we just make this convention. The span of an empty set is a 0 subspace. And that goes in line with the general result about spans, that every span is a subspace. We don't have time to see the argument, even though it's very instructive to see the argument. I'll make the upload. You will see this on the web. I'll see if we have time to discuss this. It's a new type of constructions. It's different from the orthogonal complement subspace, but it covers for the remaining 40% of the examples in the yellow book. It covers for the remaining 40% of the examples in the yellow book. Yeah, the argument is here. You'll see it later. And now we're fully equipped to do any other example on a subspace in the yellow book. Trust me, every example will fall either into the orthogonal complement subspace, span subspace, or intersection of one of the examples in one of the categories. Look how efficient we are. We just, in 1 hour, we covered all of the subspace examples in the yellow book, and there will be lots of them there. Any questions? Yes, please. It can't be. We just decided for it to be so. It's as good as like why the exponential of 0 is 1. Why is it so? Yeah. Why it is 1? Why if you take, say, number 2 to the power 0, it's 1? Why is it so? Have you ever thought of that? I mean, we know that 1, if you square number 2, it's 4. If you take a cube, it's 8, right? Because we just multiply 2 by itself n times. But when you say 2 to the power 0, you cannot multiply 2 by itself 0 times, can you? Why did you decide it is 1? This convention. I mean, this result. It's a convention. There is nothing behind this besides our joint agreement that we're going to treat it like this. And again, we make this decision for the only reason that if you make this convention, it works nicely with the other properties of the exponentials. For instance, this property. This property. If you don't make such a convention, if you say this is say 0, what's wrong with this convention? Can you make such a convention? Yes, you can. This is as good as the other one. This is as good as this convention. I mean, when you make a convention. But when it comes to this, you will realize that this is better. Because if you make this convention, This will break. This identity will break if you set one of the m or n to 0. So it's a convention. You can make it, but it's bad because it ruins many properties of the exponentials. Whereas this convention doesn't. So when you make a convention, you make it comfortable to you. That's the only reason. That's why making this convention for the span, it makes it comfortable because it doesn't ruin this claim. That's the only reason we make such a convention. Any other questions? All right, thank you very much. It was a lovely lecture. I'll see you all the day after tomorrow.